Uh, Hello everyone. Welcome to Research Talk 3. Our speaker is Professor Lakshmi Prasad Natarajan from IIT Hyderabad, and chair of the session is Professor Nikhil Karamchandani. Nikhil is a faculty member at IIT Bombay. He has done his PhD from UCST, and he has done postdoc from UCLA as well as UCST. I hand over to him now. Nikhil, please.
Okay, thanks, Satyajit. Okay, and welcome everyone to the to this research talk on the second day of the summer school. So today we have Professor Lakshmi Prasad Natarajan from IIT Hyderabad. Lakshmi Prasad did his PhD from ISC and then did a postdoc at Monash University in Australia, and has since then been at IIT Hyderabad. And his core research interests are in coding techniques and information theory for communication systems. And today he's going to talk to us about some capacity achieving codes for the binary erasure channel via discrete Fourier transform. So before I let Lakshmi Prasad take the stage, just a couple of rules of engagement, I guess. So one, if you have any questions at any time, please post them in the chat box. I will be monitoring the chat box, and at any suitable point, I'll just stop Lakshmi Prasad and I'll ask him the question, and he can then answer them. You can also raise your hand using the appropriate buttons, and someone will then kind of let you unmute you, and then you can ask your question also at that point. So, as the speaker himself has told me, he would like this to be as interactive as possible. So, please feel free and ask as many questions as you want. We'll interrupt him as often as needed. Okay. So with that, yeah, over to you.
Thanks, Nikhil. And also thanks to Satyajit for uh, giving me this invitation. So this is, most of this talk will be like a tutorial, except for the last part, very short last part, which is original work with Dr. Prasad Krishnan, who is in IIIT Hyderabad. So maybe I'll start with the title. What does the title mean? So we are talking about the binary erasure channel, and this is a communication medium through which you can transmit bits, and then the channel will randomly erase some of the bits that you transmit. For example, let's say you transmit the sequence of bits at the bottom here, 0, 1, 0, 1, 1, 0. Then two of these bits have been erased. So the receiver knows which bits have been erased, and the unerased bits, the receiver knows the value. Okay. What are codes? Codes are just mechanisms which help you deal with this uncertainty in the channel, this random erasure. Right? So what you can do is something like an example that you see at the bottom of the page. Let's say what you actually want to communicate are just two bits, M1, M2. Instead of just sending M1 and M2, you also send a parity. You send M1 XOR M2. Okay, so this is M1 plus M2 or M1 XOR M2. So M1, M2 are bits, they are binary digits. M1 XOR M2 is also binary digits. So instead of sending just two message bits, you are sending three coded bits. So this is called a transmitted code word. This is what you want to push into the channel. The information is just this, M1, M2. Okay, that's the message. So this goes through the binary erasure channel. And let's say by some random event, the second bit got erased. Right? So what the receiver sees is that it knows the value of M1, M2 it doesn't know, just a question mark. So the receiver doesn't know it, but then it knows the value of M1 plus M2. So these are two equations, two unknowns, two linearly independent equations. So the receiver can solve for M1 and M2. Right? So it knows M1 already, and then it can cancel out M1 from this value of M1 plus M2. So the receiver gets M2. So you see that. So this is a coding technique, right? And this helps you deal with erasures. So this is what we will be talking about. And in particular, we will be talking about capacity achieving codes. So these are basically codes which guarantee two things. First thing, it provides reliability. Reliability means the probability that the receiver fails to decode is close to zero. Okay, so with probability close to 1, everything flows smoothly. Okay? So that is reliability. And second, most important is that while guaranteeing reliability, these codes allow you to communicate at the theoretically highest possible data rate. Okay, so these are capacity achieving codes. So in general, what you will see is that there will be a set of k message bits. You will do encoding at the transmitter, and then you will get a set of list of n coded bits, which forms a code word. You will transmit this through the binary erasure channel, and the BEC is a random channel. So I'm sorry, its output is random. So it will randomly erase some part of the transmitted code word. So the receipt vector might look like this: C1 is there, C2 is erased, for instance, right? And then the receiver will start doing the decoding. It has to guess, it has to estimate the message bits, right? And when it is doing this, maybe it is able to decode M2, MK, etc., but maybe it fails to decode M1. So this can also happen. So this will be the general setup, right? So our main idea is to design capacity achieving codes. So this is the overview. As I told you before, much of the talk is like very brief tutorial about some classical tools. Okay, so background 1, you will start with the definition of binary linear codes. Background 2, you will see how they can be used to combat erasures and what's the meaning of capacity. That's what we will see. Background 3, this comes from an independent direction. We will see how to do Fourier transform for binary vectors. And then we will look at a particular way of doing Fourier transform. It's a Fourier transform of size 3 pi. Okay? I will tell you what this is later. And then the fourth the fourth background is how do you design codes using DFT. Okay, and this will take up much of the talk. Maybe in the last 4-5 slides, we will try to put these things together, and then we will try to as a sort of application, and then we will see that it's very easy to design capacity achieving codes using DFT. So binary linear codes. So we'll start with the definition of field. So F2 is simply the set containing 2 elements, 0 and 1. These are binary digits. And we know how to perform addition and multiplication with them. Okay. So addition is simply exclusive OR. So 0 plus 0 is 0. 1 plus 0 and 0 plus 1 are both equal to 1. 1 plus 1 is 0. This is the only strange thing that's happening here. So this means that the negative of 1 is also equal to 1. Okay. That is addition. Multiplication is simply AND. Okay. Only 1 into 1 is 1. Everything else is 0. 0 times 1 is 0. 0 into 0 is 0. Okay. And basic rules apply. Like, sorry, there's a typo here. This should be AB equal to BA. Okay. Commutative T holds. There's a mistake here. Sorry about that. Distributive law holds. Multiplication distributes or addition. Inverse exists if a number is not equal to 0. Number is not equal to 0 means it should not. Okay. Inverse of 1 is 1 itself. And addition is subtraction because 1 plus 1 is 0. Wherever you see subtraction, I'm just talking about addition. So you can use F2 to create a vector space, and that vector space is called the Hamming space. So you denote it as F2 par n. This is simply the set of all binary vectors of length n. So you have vectors of this form. So I think in this talk, I will think of vectors as row vectors. So this is a row vector with n components. Each component can take 2 values. So the size of the Hamming space is 2 pi. Right? And you can do vector addition. You can define addition here. Vector addition is simply component-wise addition. This addition is over F2. Okay, A1 plus B1, this is over F2. Subtraction is also same as addition because we already know 1 plus 1 is 0. How do you multiply a vector with a scalar? Pretty straightforward. You take a vector, you have only 2 scalars because you live in F2, right? You have 0 and 1. 1 into vector is itself, 0 into vector is the all 0 vector. This is the bold 0. Okay. Right. Now, with this, and then the observation that this Hamming space is actually a vector space over the field F2, you can actually do all of linear algebra over this. For instance, you can define linear independence of m vectors. So you have m vectors A1 to am. I've written them in bold. Bold font means they have vectors. So you have m vectors from F2 bar n. Beta 1 to beta m are scalars. If the only linear combination which gives you 0 is the all 0 linear combination, beta 1 to beta m, all of them equal to 0, then this collection of vectors is linear independent. This is a standard definition, right? And then the span of a collection of vectors. Similarly, span of A1 to AM is a set of all possible linear combinations of A1 to AM. But then notice that the scalars come from F2. and subspace. Okay. So what I'm doing right now is just going through the linear algebra for binary vectors. Okay, that's all we are doing, and then somewhere in between we will introduce coding theoretic terminology. Okay, so now we briefly recall subspace. A collection of vectors in the Hamming space, you say it is a subspace if it satisfies this property. It should be closed under vector addition. What do I mean by that? If C is a collection of vectors and then it satisfies the following property. You pick any two vectors from C, call them A and B, and then you add them. Remember, addition is component wise, and if this added, the sum vector A plus B also belongs to C. Okay, irrespective of how you pick A and B, then we say that this collection of vectors C is a subspace. Okay, so here is an example. So I am in F2 part 3, 3 length vectors, and then I'm looking at the collection of vectors, sum of whose components is equal to 0. Okay. Let's say I do it manually, I solve this, and then I figure out that out of the 8 vectors here, only 4 of them satisfy this condition, and these are the 4 vectors. And it's easy to check manually that this is indeed a subspace. For instance, if you pick these 2 vectors, second and the third vector, you add them, you get the fourth vector. Okay, so this is indeed a subspace. Now you can go ahead and then you can define basis, dimension, etc. A basis of a subspace is simply a collection of vectors which are linearly independent and whose span equals a subspace. Right? And this is a standard definition we know from matrix theory or linear algebra course. And similarly, the number of vectors in this basis, that is the dimension of the subspace. What is somewhat new, if you have not looked at Hamming space before, is that the entire space is finite, and the collection of vectors in a subspace that is also finite, and it is related to the dimension as follows. The last line you see here, the number of vectors in a subspace is 2 to the power of dimension of the subspace. So here is an example. So this is the subspace we saw in the last slide, and these are the 4 vectors. I've written them row wise. You see that there are exactly 4 vectors. So the dimension of the subspace is 2. 2 part 2 is 4, and this G1, G2 forms a basis. Okay. So now we can define. We are in a position to define linear codes. The definition is very simple. Okay. So the definition is a binary linear code is a subspace of the Hamming space. That's all. Okay. So if you do linear algebra or math, you will call it subspace. If you are a coding theorist, you will call it a binary linear code or code for short. Right. So on the right hand side, you see a code of length 6. I have stacked the code words one on top of each other. So these are 6 length vectors, and the dimension is 3. There are exactly 8 vectors. Okay, so the standard terminology in coding theory, some basic terminology. This collection of vectors C, you call it a code or code book. The vectors in C are called code words. The capital N, so the length of the vectors, that is called the block length of the code, or simply length, and K will be used to denote the dimension. Okay. So once you have a code, you can define what is known as a generator matrix. Generator matrix for a code is simply a matrix. Let's say a code has dimension K, length N. Then the generator matrix will be of size K cross N. It will be a fat matrix, and the rows of the matrix will form a basis for the code, basis for the subspace. Right? So you simply stack them one on top of each other. Let's say G1, this is the first row, G2, G3, Gk. Okay, they form a basis for the code. Why is it useful? There are several places in which you tend to look at the generator matrix. One example is that you use generator matrix for encoding. Okay, so let's say you have K message bits at the transmitter, and you want to generate a code word. What you do is that you take this message vector M. It's a 1 cross K row vector, right? You multiply this with the generator matrix G. Right? So you have 1 cross K row vector multiplied with a K cross N matrix, you get a 1 cross N vector. That is a code word. Okay? Code word is something that you transmit. So that is C. Example, same code that we looked at earlier, then 6 dimension 3. This is one of the generator matrices of the code. Okay, the rows generate the subspace. They form a basis for the subspace, and you can use it to encode. Since the number of rows is 3, you can encode 3 message bits. So the message here, the vector contains 3 bits, M1, M2, M3. How do you encode? You simply do vector into matrix multiplication, M into G. And if you simply expand this, you use M1, M2, M3 for vector M, and then you use this particular matrix for G, and then you expand. This is the This is the thing you get. This is the expansion, and this is the vector that you transport. Okay, so this is nice. So now we have a introduction to binary linear codes. So in case you have any questions, this is probably a good place to stop. Otherwise, we can proceed to the next section.
So I don't see any questions in the chat
Okay.
right now, and don't seem to be any raised hands either. So maybe we can proceed.
Okay, Nikhil. Thank you. So next part, we will see how codes are useful in correcting erasures. I won't go very deeply. I just want to give you guys a taste of how this erasure correction works, and we will review the idea of capacity. Right? Okay. So let's look at the example that we did before. So we had a code of length 6, dimension 3, and let's say I'm using that code to perform digital communication. Right? So you see a picture here. The top half is a transmitter. The bottom half is a receiver. They are connected through a binary erasure channel. This particular channel, what it does is that it will randomly erase some of the components which have been fed into it. Okay. At the transmitter, the objective is to communicate 3 bits, M1, M2, M3. But then I'm doing encoding. I'm using my error correcting code or erasure correcting code, the binary linear code. So I multiply this with the generative matrix that we saw before, right? So the code word that I get is this. You see that these are all, each component is some combinations of linear combinations of M1, M2, M3. So this is the 6 length vector that I push into the channel. And let's say, for instance, these components have been erased. Okay, first, second, and I think fifth component has been erased. The receiver is able to look at the values of the remaining components. So what does the receiver do? It has to, the objective of the receiver is to decode M1, M2, M3. That's what the receiver wants to do. Can it do it now? I think it can. So it knows the value of M3 from the channel. So M3 it can decode. Using M3 and the value of M2 plus M3, it can decode M2. Okay, so M3, M2 both have been decoded. Using M2 and the value of M1 plus M2, it can decode M1 also. So the receiver is able to decode M1, M2, M3. Okay. So I think we can all agree that this erasure correction has been possible only because we use this particular code. Right? Had you simply transmitted M1, M2, M3, and let's say 2 of the 3 bits got erased, then you would have lost information. But then things are not always good. Even this coded system is susceptible to failure. Okay, so let's say the same example, but let's say the channel erased 4 bits. So the receiver only knows now value of M1 and M2 plus M3. What does it do now? It can definitely decode M1. It has it from the channel output, no problem. But then the only other information it has now is the value of M2 plus M3. Okay, so the receiver knows the value of M2 plus M3, the sum, but it doesn't know the value, individual values of M2 or M3. So the receiver gives up. So the receiver says question mark, I don't know. Okay. So how many erasures now? 2 out of 3. Okay. You are successfully able to decode only 1. So even this is possible even when you do erasure correcting mechanisms. Right? So in general, what will happen? So let's say you're using a code of length capital N, dimension capital K. Now what do? You take K message bits because your dimension is K. And then for the code word, you simply multiply the message with the generator matrix. You get a n code word. You transmit it through the binary erasure channel. Now the binary erasure channel works as follows. So there is a parameter called epsilon, which characterizes this channel. This is simply the probability with which the channel will erase each component. Okay, so the ith component gets erased with probability epsilon, and the ith component remains unerased with the remaining probability, which is 1 minus epsilon. So this epsilon characterizes the channel completely, and this is called the channel erasure probability. So the receiver observes this partially erased code word which was transmitted, and the receiver will try to decode. So when it is trying to decode, maybe it is able to decode some message bits like M1, MK. Maybe it is unable to decode some message bits like M2. So this is what will happen in general. Right? Now we characterize the system using.
So Lakshmi Prasad, maybe before you move on, there are a couple of questions from Saraswati from IIIT Delhi.
Okay.
So the first one is, how can we create the generator matrix for a code?
Okay. Maybe, okay. So generator matrix is simply so you characterize it by its rows. So the rows should form a basis. So what you do is that you go to the subspace and then you have to create a basis from the subspace. So there are like several ways to do this. So any linear algebraic technique that you know of can be used. For instance, one very naive way to do it is that you list all the code words from the subspace, and then you do, let's say, row reduction. Okay, if you do row reduction, you can get a basis. So that is one possible way to do it. There might be other ways to do it based on the code definition. Just by looking at the code definition, there might be simpler ways to create a basis. But this is one technique which will work always.
And I think another question from her was, so what is the use of the Erasure code, or how does the reliability increase when you use essentially an Erasure code?
Okay, so I think we kind of saw this in this example. There are ways to actually analytically characterize how useful the Erasure code is. We will introduce those parameters next. Okay, but then what is exactly happening is that when you use the Erasure correcting code, you are adding some redundancy. So actually, you want to communicate only M1, M2, M3, but then you are sending some more pieces of information. So apart from M1, M2, M3, I'm also sending the value of M1 plus M2, M1 plus M3, M2 plus M3. So even if, let's say, one of them gets erased here, you have still enough information to decode M1, M2, M3. So that is exactly what is happening.
And I think a related question from Srinivas from NUS is, in this particular example, will it work for any 3 erasures? This particular code.
No, it will work for some 3 erasures. For instance, let's say you erase the last 3. Say whatever I have highlighted gets erased. It's clear that is no problem. But let's say you erase the first 3, then you end up with some. The receiver will not be able to decode. So what you have is M1 plus M2, M1 plus M3, M2 plus M3. 3 equations, 3 unknowns, but these 3 equations are linearly dependent, so you cannot solve it uniquely. But then this code can correct any 2 erasures. You pick any 2 components, erase them, this code will be able to correct it.
Yeah, I think these are the questions at the moment. So
Okay.
yeah, we can continue.
Okay, Nikhil, thank you very much.
Yeah.
So, okay, so going back, so these are the 2 parameters that we will be interested in when we are talking about the code. The first parameter is the rate of the code. The rate of the code tells you how efficient the code is in using the channel resource. Think of channel as a resource, and then you see how much information that you're conveying. Right? So in this general setup, right, what is happening? You are sending k message bits. Okay, so the information content is k, and then how many bits are you actually transmitting? Coded bits, you're transmitting n, right? So there is this uh, uh, redundancy that is creeping in. So this ratio k by n that characterizes how efficiently you are using the channel. So that is called the rate. So if k by n is more, then your data rate is higher. If k by n is smaller, then you can think of the data rate being smaller. So usually we want rate to be as high as possible. That is one. Second is the bit erasure rate, BER. So this is what we will be focusing throughout this talk. So the BER is simply on the average, what is the fraction of message bits that you are not able to decode. Okay, so that is the bit erasure rate. So we would want the BER to be as small as possible, rate to be as high as possible, and as you can expect, there is a tension between these two. Okay, so typically there are 2 performance metrics in the literature given in practice. The first is bit erasure rate, BER, that we just talked about. This is simply on the average how many bits you are not able to decode. So you count the number of I such that mi hat is question mark, you are not able to decode, divided by k, that is a fraction, and then you take the expectation. Expectation because the channel is random, right? Because the channel is randomly erasing coordinates, that's why you have to take expectation. Block erasure rate, you say that that is a block erasure if the receiver is unable to decode even one message bit. Okay, it's a much stronger condition. You have k message bits. If the receiver is unable to decode even one of them, then you declare a block erasure. So block erasure rate is a property that this will have. So you can show that the BER is always upper bounded by block erasure rate. So whenever people define capacity, they define it in terms of block erasure rate. This is typical, but in this talk we will take a weaker stance. So we will talk about bit error rate being close to 0 for reliability. Right. So I told you before that there is a tension between the BER and the rate. One of the ways to talk about it is by talking about the fundamental limit for reliable communication. So this was characterized by Claude Shannon way back in 1948. So this is his result. Okay. So going back, remember that we said that we do reliable communication if the bit erasure rate BER is close to 0. Right? So Shannon tells you when this is possible. So Shannon tells that BER can be driven close to 0 only if two things happen. Okay? One is that the block length that you're working with, you have to keep increasing it. If you have a finite block length, you cannot make BER go very close to 0. That's not possible. So if you want to drive BER to 0, first you have to keep increasing the block length. So n goes towards infinity. That is one. Second, the rate at which you communicate should not be too high. So that's an upper limit to the rate. That is 1 minus epsilon. Epsilon, remember, is a property with which the channel will erase a component. So basically, 1 minus epsilon is roughly the number of components that go through unerased. Right? So Shannon says that R should be less than 1 minus epsilon, and the block length should go toward infinity. Okay. So this highest rate, to be technically correct, the supremum of all rates through which at which you can communicate reliably, that is the capacity of the binary erasure channel. So if somebody is talking about capacity, they mean this one, 1 minus epsilon. And what do you mean when you say we achieve capacity, right? So what we mean is the following. You want block length to go towards infinity, BR to go down to 0 if R is less than 1 minus epsilon, or equivalently, if epsilon is less than 1 minus R. Right? This is the things that you need to happen, right? So if you want to achieve capacity, theoretically, this is what you need to do. You have to construct codes for rate R. Let's say you fix some rate R. You want to construct codes for rate R. And then you have to construct not just one code, but several codes for longer and longer block length. One code for block length 2, another code for block length 3, another code for block length 4, so on and so forth, for increasing block length. So you have an infinite sequence of codes, all of rate R, such that if you look at their BR, it goes to 0 as the length increases if epsilon is less than 1 minus R. Okay, this is what we want. I will write down formally. So, but before writing formally, I will show you what this looks like.
So, Prasad, maybe before you go there, firstly, there is a request to maybe explain those BER and block erasure rate again.
Okay.
And one question I had about them was, so these are defined in terms of kind of the number of kind of undecided message symbols at the output, right? But what if I I have output some estimate for them? It's just that that estimate does not match what the true message bit was. So in particular, I mean, essentially, I'm asking. This is like the bit error rate versus what you are calling a bit erasure rate, I suppose. So what's the distinction, and how do you deal with that? Perhaps you can explain that also when you go over those concepts.
Okay, so maybe I will start by answering your question.
Sure.
So what happens when you have an erasure in the decoding part is that the entropy of that bit that you are not able to decode, given the channel observation, that happens to be 1 in the standard setup. Okay. So that means if you are guessing randomly, then with probability half you will be correct. So in that case, the bit error rate would be equal to half of bit erasure rate. So that is a straightforward relation. So we can focus on BR or bit error rate, whatever is works. Both will be equal. Going back to the definition of bit error rate, you can think of it as follows. Maybe you can think of it like this. So let's say you communicated k bits, and the receiver is trying to decode k bits, and then you ask the probability. Let's say you look at one of the bits. There are k bits transmitted, right? You look at one of the bits, and then you ask the probability that what is the probability that the receiver will not be able to decode this bit. Okay, so that is, I'm writing it like this. So this is exactly what I said. P of mi hat equal to question mark is the probability that the receiver is not able to decode the ith message bit, right? Now there are k message bits. Then in general, maybe all these k probabilities could be different. So you simply take the average, right? So this means on the average, what is the probability that you are not able to decode one of the k bits? So you can think of BR in that way also. Okay, so that is BR. Block erasure rate is a probability that you are not able to decode the entire block. Okay, so let's say you communicate M1, M2, M3, right? The receiver is able to, okay, maybe I can show it using this example. I think this will work. Right? So in this case, there are no bit erasures and there is no block erasure. The receiver is able to decode the entire block. In this case, 2 out of 3 bits got erased, but it's one single block erasure. You transmitted one block, the receiver is not able to decode the entire block, so you think of this event as one block erasure. Right? So now going back, this block erasure rate is simply the probability that you are not able to decode the block completely. That's all. So Nikhil, did I answer all the?
Yeah, you did. You can go ahead.
Okay, so thank you. Right. So you can see this just to have a pictorial way of remembering about capacity. So let's say you have a sequence of 4 codes, C1, C2, C3, C4, block length N1, N2, N3, N4, and then you are looking at their bit erasure rate. So let's say you're plotting this curve. This is the first code with block length N1. On the x-axis, you have the channel parameter epsilon. On the y-axis, you have the BR. Now, epsilon will range from 0 to 1. Epsilon equal to 0 is a good channel. There are no erasures. Epsilon equal to 1 is the worst channel. The channel will simply erase everything. Epsilon in between is intermediate. Okay. So as you vary epsilon, BR will increase. So the channel becomes bad, so the BR will increase. For this particular code, this is what the BR looks like. Right. Now, let's say I go to a slightly larger length, then you see that the BR will become, the curve will become slightly steeper. Okay. In case you're using good codes, that is, it becomes slightly steeper. You go to slightly larger length, it will become even more steeper. Even larger length, it will become even more steeper. Okay. What we are looking for is some sharp transition like this. Right? But the transition should happen exactly at 1 minus r. Okay, because this is the point which satisfies the condition r is equal to 1 minus epsilon. That is the capacity, right? So epsilon equal to 1 minus r. If epsilon is less than this knee that you are looking at, this transition point, then the BR should be small. Above that, what happens, I don't care. Okay, because that is the capacity. Right? So we can define this formally. So you consider a sequence of codes, C1, C2, C3. They're all separate codes. Okay, they are different subspaces. They have their individual dimension and length, K1, N1, K2, N2, etc., etc. And this sequence of codes is of increasing block length. Okay, this we have to necessarily consider because Shannon says n should go towards infinity. Right? So the block lengths are increasing, and then their individual rates, they will converge to a particular value r. Okay, this means that you are trying to communicate at rate r. So we say that the sequence of codes is capacity achieving if 2 things happen. I mean, no, only one thing happens. The sequence of codes is capacity achieving if for any channel erasure parameter epsilon less than 1 minus r. So this comes from the capacity statement, Shannon statement. If epsilon is small enough, it's less than 1 minus r, then the BER of these individual codes, right, that should go down to 0. Let's see this here. So this is 1 minus r. This point is 1 minus r. So let's say I pick an epsilon here, and then I consider, so this is my epsilon. So let's say I go down the sequence of codes. Here BR is slightly higher. Here BR has come down further down. This is almost close to 0. This should happen for every epsilon less than 1 minus r. This is what we are looking for.
Okay. So one question regarding this definition itself, I guess, is from Milan from IIT Bombay. He's asking about the possibility of zero error codes in erasure channels instead of vanishing.
Okay. So that will lead to a completely different problem statement.
Okay.
So zero error codes means you will be talking about minimum distance. So that's when you the okay. So basically, zero error means no matter what erasure pattern you have, you should be able to decode successfully. Okay, there is no probability or stochasticity in the system. Uh, so the uh, minimum distance comes into the picture because if you have a code of minimum distance daemon, then you can correct any erasure pattern of number of erasures at the most daemon minus 1. So that will lead to a different set of fundamental limits, like Gilbert-Varshawa bound, etc. Okay. So here the problem statement itself is different. So code which is good for that setup may not be good here, and vice versa.
Okay.
Okay. So one main problem in coding theory is to design such codes, capacity achieving codes, theoretically prove that they are capacity achieving. Okay. So this is a list of well-known capacity achieving codes for
May
binary
I,
channel.
may I ask one question?
Sure.
Yeah. So, are you also looking into the how fast this convergence is?
Not right now. So we have uh, again there are some optimal conversion rates, uh, but we have not worked on it. I mean, we don't have results on it, and also this talk will not talk about it. But that's a very good question. So some of the codes that I will show in the next table, they may or may not have optimal convergence rates. They are
Okay.
just optimal in sense of capacity and in terms of BER, not the block erasure rate.
Hmm. Okay. Yeah. Thank you.
Thank you. So these are the codes so far known, which are capacity achieving for the BEC from the perspective of BER, which is weaker than the perspective of block erasure rate. Okay. So I'll be talking about the last thing here, which is very easy to design if we know the correct tools. Okay, so that's what we are trying to do. Okay. So that is the end of the second section. Third section is the next background. Okay, so how to do Fourier transform for binary vectors. Um, Okay, so there are several ways to do, several definitions of Fourier transform based on how you define convolution in time domain. So in this talk, we'll be looking at one particular way to do DFT, and we call this the m-dimensional DFT of size 3 parallel. So I'll tell you what this is. But before that, we would like to draw some parallels between what happens when you do DFT of real signals versus what happens when you do DFT of binary signals. Right? So let's maybe look at the left-hand side first. Let's say you have an n-dimensional real signal and you want to do DFT. Okay, the Fourier domain, so in the frequency domain, the signal will lie in the complex field. Right? Although the time domain signal itself is real, the Fourier domain signal will live in the complex space. Right? Why does this happen? Because to do DFT, we require some specific roots of unity, and those roots of unity are found in the complex plane, not in the real line. Right? So suppose the time domain signal is like this. Bold A denotes a complete signal. AI is the ith time component. A hat is the DFT. A hat J is the jth frequency component. Because this signal is real, you will see conjugate symmetry in the DFT. The value of DFT at frequency n minus j is the complex conjugate of the value of the DFT at frequency g. Something exactly parallel happens for DFT of binary signals. To do DFT of a binary vector, you need some specific roots of unity. For the example that we are going to see, you need third roots of unity. They're not available in F2, but in some other field, a larger field called F4. You look at it next. So although the time domain signal will be over F2, the frequency domain signal will be over a slightly larger field, F4. This is similar to what happens in the real signals. Similarly, you have conjugate symmetry, okay, but that is expressed in a different way because you are living in a different universe. The DFT value of the DFT at frequency 2j is square of the value of the DFT at frequency j. So that's how the conjugate symmetry comes into picture. Okay. So what is this finite field F4? So we need to know this. So in the yellow color, I have highlighted the addition and multiplication tables of the binary field F2. This we have already seen. To go to F4, what you do is that you include one imaginary number. Okay, let's say you call it alpha. Alpha is an imaginary number, and then it has to satisfy certain properties. Only then this thing will work out. So what are the properties it satisfies? Alpha plus alpha should be 0. Because 1 plus 1 is 0, so you want this to be true as well. Alpha square is 1 plus alpha. Okay, this comes from irreducible polynomials, but let's not go in there. Alpha square should be 1 plus alpha, and alpha cube equal to 1. So these are the rules. Right? So if you impose these rules and then you do addition table and multiplication table, this is the table you will get. And you can believe me when I say that if you know these three statements, you can do arithmetic over F4. It's pretty straightforward. Okay, so now you can do addition and multiplication over F4, finite field of size 4. What is important for us is that it contains the third root of unity, alpha cube equal to 1, right? So alpha is the third root of unity. Now that is about F4. Now we have to talk about time and frequency. What is time? What is frequency? So we will consider time and frequency as m dimensional. Okay, when you do DFT, signals and systems, you do one dimension. Time is one dimensional. Frequency is also one dimensional. Here you think of time and frequency as multi-dimensional, m dimensions. In each dimension, time and frequency can take only 3 values. So these 3 values are 0, 1, 2. Put together, this set is called Z3. Okay. And in each dimension, time is cyclic. Start from 0, hop 1, hop 2. You take one more hop, you come back to 0. So 0, 1, 2, 0, 1, 2. Okay. It's a cyclic shift. Right? So to capture this cyclic shift, you can define addition and subtraction in Z3, which is modulo 3. So I plus j is simply integer addition of I and j modulo 3. Similarly for subtraction, and time and frequency, you can simply define them as vectors over Z3 and vectors of length m. They are m dimensional. So this is what time would look like, time or frequency. If m is 2, then time looks like this. There are 9 time instances starting from 0, 0 to 2, 2. If m equal to 3, you have a Rubik's cube. So there are 27 time values, 27 frequency values. And this is how you index a vector in time. Okay, so let's say you have a binary vector of length 3 per m. You can think of it as a vector in the Hamming space. At the same time, you can index it like this. So a suffix vector I, where vector I runs over that m dimensional time space. So for m equal to 2, this is what the vector will look like. You can think of it as a tensor, for instance. Similarly, frequency domain, A hat is DFT, so it lives over F4. And then the indexing is over J. J runs over Z3 per m. Same thing, but then I'm putting a hat, same m dimensional space. Okay. Now, how do you do DFT? There's a well-defined DFT formula. These are classical tools. You will use one of the frameworks, more recent frameworks, which are introduced by Professor Natarajan and his PhD advisor, 1992, and they give an explicit formula to do DFT. This is a standard way, right? So this is the DFT at frequency J. How is it defined? Sum over all time instances I. You take AI, value of the time domain signal at I. Alpha is the third root of unity. So alpha to the power of time into frequency, I into j. And this I dot j is simply the dot product, right? So that's what you do. Similarly, you can do inverse DFT. AI is summation over all j, all frequencies. You have aj hat, value of the DFT at frequency j, alpha bar minus I times j. Okay. So it's a clean DFT and IDFT formula. And now you know everything. So you know how to work with F4. What is the forward DFT? What is the inverse DFT? We know all the formulae. And you can do DFT pairs. For example, if this is the time domain signal, this is m equal to 2, you can find the DFT. This is the frequency domain signal.
So, Prasad, can you go back one slide? So, yeah, here, where is the m? How is the m appearing here in these representations?
You mean small m?
Yeah. So, like this m-dimensional DFT. So, is the m? Yeah, I'm not. Is this picture for like m equals 2 or?
Yeah, sorry. Yeah. So this picture is for m equal to 2.
Okay.
Correct. Sorry about that.
I see. Okay. All right.
Sorry about that, but thank you. Picture is for m equal to 2. Formula is in general.
Okay.
Sorry about that. And again, this example is for m equal to 2. Yeah, so it's pretty straightforward to use the formula. And you have some standard, what you expect is indeed happening. There is linearity. If C is A plus B in time domain, in frequency domain, C hat is A hat plus B hat. This is a convolution in time domain. You convert two time domain signals A and B, you get C. This is a formula. In frequency domain, you do point-wise multiplication. Reverse also happens. Convolution in frequency domain is point-wise multiplication in time domain. And this conjugate symmetry. If A is a binary vector, then A hat of 2j, right? 2j means j plus j. A hat of 2j is A j square. This is conjugate symmetry. So that's the end of the third background. We are moving into the fourth background. How do you use DFT to construct codes? So what I'm going to present is a classical technique. It's a very old coding theory technique. And this is one of the ways to study a much broader class of codes called abelian codes or group codes. Okay. Right. So something before we go into equations, etc., construction. So I was telling you this is a very old coding theory technique, designing codes in the frequency domain. So these are some of the references: Bowman, 1967, Camion, McWilliams, Blahoud. So Blahoud's textbook, it reads BCH codes and Reed-Solomon codes in the frequency domain. So we are doing exactly the same, but for a different class of codes. So this is a very general technique, but then we are looking at a specific case where you index time and frequency by Z3 param. In general, you can replace the Z3 param object with any abelian group of odd order. Okay, but we won't do that in this talk. Remember, we what we will do is we will index code words like this. We'll be looking at block length 3 param, and then we will index code words like this. Ith component, I runs over Z3 param. How do we design codes? We design codes as collection of band stop signals. So what we will do is that we will identify a collection of frequencies, and then we will look at all time domain signals which have zero DFT value in those frequencies. That's how I define my code. Okay, so this collection of frequencies where you want to impose zero DFT, I will call it the zero set. Okay, so remember now this Z3 param, think of it as frequencies, and this calligraphic Z is a subset. You identify a small subset of those frequencies, you call it zero set, and then using this Z, you construct a code, right? So I'll denote that code as C DFT of Z. To remember that we constructed this using DFT. What is the definition? You look at all time domain signals of length 3 param which have zero DFT value in these collection of frequencies. That's it. Right? But then remember, conjugate symmetry, which means that C hat of 2j is C hat of j square. So this means that if j belongs to z, 2j should also belong to z. Okay, because if Cj hat is 0, then C2j hat is also 0. So z should have this property. It should be closed under multiplication by 2. Okay, this is one example. So this is an example where m equal to 2, and I'm choosing z as all the frequencies apart from two frequencies, 1 and 2. So 1, 1, 2, 2 are here. All the 7 frequencies put together, I'm taking it as a zero set. So my code words in the frequency domain, they will look like this. You have zeros everywhere except these two. This is 1, 1. This is 2, 2. 2 times 1, 1. So if you have DFT C hat 1, 1 here, the DFT here should be C hat square 1, 1. Right? So all my code words will look like this. And they are parameterized by a single scalar, C hat 1, 1, which takes value from F4. F4 has 4 values, right? So there are 4 possibilities for C hat 1, 1. So I have exactly 4 code words. So this is a code which consists of 4 code words, which means its dimension is 2. Length 9, dimension 2. And I did some manual work, and then I found out what these 4 code words are, because I know the DFT IDFT formula, and these are exactly the 4 code words for this example. Okay, so we will look at some properties for these codes. So first property says that if you pick any 0 set with the property that we want, it should be closed under multiplication by 2, then 3 things are guaranteed, basic things. Particular code will be a binary linear code, guaranteed. Block length is 3 parm, that we know it's straightforward. And then the dimension of the code, that will be 3 parm minus the number of the size of the 0 set. Okay, so it's very easy to identify the dimension and length of the code. Right? So in the remaining slides, we will be focusing on the symmetry properties of the code. Okay, we won't talk about minimum distance at all, because we'll be using a recent result. It says that if a code has sufficient symmetry, then it will be capacity achieving. You don't have to talk about minimum distance at all. So we'll be talking about symmetry only, okay, from here onwards, right? So if you're talking about symmetry, you have to talk about permutations. So what is a permutation? So let's say pi is a map from Z3 parm to Z3 parm. So you can think of Z3 parm as either time or frequency, right? So Z3 parm to Z3 parm, and it's a one-to-one map. Okay, it's on to injective and subjective. Okay. Now, if you have such a map, it's called a permutation. That's all. And you apply it on the vectors. How do you apply it? So let's say C is a vector. I permute the vector. I permute the coordinates as follows. So pi of C, instead of having component Ci, it has component C of pi n. Okay. Or in other words, if A is pi of C, then the ith component of A is the pi of ith component of C. So you simply write down all the entries and then you shuffle them based on pi. So that's a permutation. Right? How does it interact with the code? We say that a particular permutation is an automorphism of a code if it satisfies this nice property. You pick any code word, you pick any C from your code, then pi of C should also belong to the code. So you pick a code word, you permute it, and the resulting time domain signal should also belong to the code. If that property is satisfied, when you say that pi is an automorphism of the code. Each code can have several automorphisms, and the collection of all the automorphisms of a code is called the automorphism group of code. So we will denote it as aut of C. This is a set of all permutations which preserve the code. And we want codes with symmetries, and with a lot of symmetry, and highly symmetric codes have very large automorphism groups. Okay. So this is one example. I'm applying this particular permutation. Pi of I is defined as I plus 0, 1. So these are the 4 code words in my code that we designed like a few slides back. If we apply this permutation, this code word maps to this code word. Second one maps to this one. Third one maps to this. Fourth one maps to this. And you can check that in each case, all the matrices, tensors that you see here, they also belong to the code. So this particular permutation is an automorphism of this particular code. Right? Now, we will look at a set of 3 properties. This will be useful in actually identifying capacity achieving codes. So the first property is called transitivity. So the observation that we make is as follows. So transitivity implies one level of symmetry. This is property 2. Property 3, 4 go beyond transitivity. They provide you more symmetries. Right? So transitivity. This property says that any code that you construct using this DFT technique has the following property. What is that? You pick any 2 time indices, J and K, then there is a code automorphism which maps J to K. Okay, it's a very strong statement. You pick any 2 time indices, J and K, then no matter what you pick, there's a corresponding code automorphism which maps J to K. Right? So this symmetrizes the code in one stage. Such codes are called transitive. So our observation is that all codes designed from DFT are transitive. Now we want some more symmetries. So I call those properties P3, P4. Property P3 is this. So beyond property 2, let's say the 0 set satisfies the following condition. The condition is that you pick a K between 1 and M. You pick a vector J from Z, the 0 set. You pick a frequency from Z. You multiply the kth component only by 2, and the resulting vector also belongs to Z. So if Z satisfies this condition, then it has some more automorphisms. So we have identified those automorphisms. So these are they look like P3 only. You pick a time domain index I, multiply only the kth component by 2. So this gives you a permutation, and this is a code automorphism. Similarly, P4, if Z satisfies the property that you pick any vector J belonging to Z, you shuffle the coordinates whichever way you like. Simply shuffle them in any way you like. The resulting vector also belongs to Z. Then we identify some more automorphisms. If Z satisfies this condition, then you have the following automorphism. You pick any time domain time domain index, I1 to IM. You shuffle it whichever way you like. That gives you a code automorphism. Okay, so basically what we reviewed is a very classical technique. We made some simple observations here. Property P3, P4 is what we observed, and that was enough for us to construct capacity achieving codes. So we are in the last section of the talk. Okay, so let's see how this is done. So again, I won't go in much into the details. I think we have around about 5 minutes, 5 to 7 minutes left. So I'll just give you the taste of the results. Okay, how do you design? So what we rely upon majorly is one of the very important results, a very powerful result by Santosh Kumar, Robert Kanderbank, and Henry Pfister from ICT 2016. The result means that if you have codes with sufficient symmetry, then you can achieve BC capacity using those codes. And this is based on a result from analysis of Boolean functions. So Kumar and others, they use a parameter called omen to measure how symmetric a code is. Right? So I'm going to define omen. So this is omen for a given code. Okay, so how is it defined? Let's go into this equation, right? So I'm looking at automorphisms of the code which fix 0. So pi of 0 should be equal to 0, right? So among all code automorphisms, look at only those for which pi of 0 is equal to 0, right? And then you let it act on the ith coordinate. Okay, so you have time domain index I, which is non-zero. You let all such automorphisms act on I, and then you look at how many different time indices you get. Okay, so that is basically the size, right? And then you take the minimum over I, all I which are not zero. Right? So that is called omen. So this is the minimum orbit size under a subgroup of automorphisms. And if this omen is large, it means that your code has high symmetry, very large symmetry. Okay, so Kumar, Kanderbank, and Pfister's result is as follows. So you go to the setup we had before. You have a sequence of codes whose dimensions are increasing, strictly increasing. Rates are converging to a value R, which belongs to the open interval 0, 1. They have this powerful result that as long as the sequence of codes satisfies two conditions. Condition 1, C1, C2, etc. should be transitive. All the codes should be transitive. Second, their omen values should diverge to infinity. Okay? As long as these two conditions are met, then this sequence of codes is capacity achieved. So this is a very algebraic condition, and we can easily meet it using DFT. Okay? So this is our construction using DFT. This is what we do. So you want a sequence of codes, right, of length 3 par m. So for each value of m, we will give a code, right? So you make m go from 1, 2, 3, etc. Then you have codes of length 3 par 1, 3 par 2, 3 par 3, etc. How do you identify the code? Using the 0 set. Okay? So in dimension m, frequency dimension m, you identify a 0 set zm. And zm, it has to satisfy the properties P3, P4 that I mentioned before. Right? Multiplying one of the components by 2, shuffling the coordinates of a frequency vector, those properties P3, P4. Zm should satisfy them, P3 and P4. And 2, the fraction of zeros that you are imposing in the frequency domain, if you take the limit as m going to infinity, this sequence should converge to a value between 0 and 1. Okay, it's very mild. So condition 1 will make sure that the omen values are going to infinity. Condition 2 will make sure that your rate converges to a particular value. Okay, so this is the rate. Rate is 1 minus this limit that you see in point number 2, right? And the sequence of codes achieves capacity. What we do is we simply get a lower bound on omin, and then we show that this goes to infinity as block length goes to infinity. And then we can also construct such a sequence of codes for any desired value of rate. Anything between 0 and 1, we can design codes using this procedure. Okay. So that is the end of the talk. To conclude, what we did was we very quickly reviewed a classical technique to design codes in frequency domain, and then we used a powerful result by Kumar Karamchandani and Pfister, which relates symmetry to performance in BEC channel. And this is the same universe of framework which was used by Kudekar, Kumar, Mondale, and others to show that read-Muller codes achieve BEC capacity, which was a famous result. On the side, we also observed that it's rather easy to design codes with symmetry in frequency domain. That's why we are able to do this very simply, just by putting all the ingredients to it. This leads to a lot of open questions, like are there other algebraic techniques to design capacity achieving codes? Can we use these codes to achieve capacity in other binary input channels, like binary input AWGN or binary symmetric channel? What happens to the block error rate of the codes we just saw? Can we decode them using low complexity decoders, etc.? So, thanks to my institutional and financial sponsors, and thanks to the audience for listening to the talk, and thanks to Satyajit for invitation. Thank you.
All right, thanks a lot, Lakshmi Prasad. Are there any more questions?
Okay.
So maybe while we wait for others type in questions. So you initially had this had a list of codes which achieve capacity of the binary erasure channel. So
Yes.
amongst those, do you know which ones actually satisfy these symmetry properties, and are there ones which don't satisfy but still achieve capacity?
It's very easy to construct codes which do not satisfy the symmetry capacity.
Okay.
For instance, let's say you have two different codes which are individually capacity achieving.
Uh-huh.
You can simply put together them. You can horizontally concatenate them, and then you can.
Oh, I see. Okay.
But coming to your other question, the codes starting from here, Friedmuller
Hmm.
codes and down, they all have these symmetry properties. But I think right now people are also interested in the symmetry properties of polar codes. Like what are the automorphisms of polar codes? How does it influence its decoding, etc. But I'm not
Okay.
very sure about the results. I'm
Okay.
not very well versed.
I see. Okay. Okay. So I don't think I see any other questions chat. So okay, then yeah, let's thank our speaker. Thanks a lot, Lakshmi Prasad.
Thanks, Nikhil.
It was great. Okay, so I do see one question by the way. So he says it's from Murad, and the question is: do you have any target application in mind while designing these codes?
Hmm. So one of the very interesting avenues at this point of time is to design codes for moderate to short block length. Uh, that's where things are very open now, because the codes that you see on the top, like ADPC codes or the ones before that, which perform close to capacity turbo codes, specifically designed for large block lengths, like block length going into thousands or tens of thousands. The block length is less than that. Things are not clear about which codes are best. In really short block lengths, algebraic codes perform really well, like BCH codes or Reed-Muller codes. They perform really well, but then it's very difficult to decode them. We don't know of a low complexity decoder. So we do want to see if we can get in that direction. but that was not the intention when we started solving this problem. The intention was to enlarge, to see how widely we can enlarge the class of capacity achieving codes and how general they can be. For instance, the class of Berman codes, they generalize Reed-Muller codes. So Reed-Muller codes are a small subset of Berman codes. And we were able to show that not just Reed-Muller codes, but this larger set of codes are also capacity achieving. So that's all I have for.
Okay. One question from Lalita is whether these ideas can be extended to other BMS channels.
So Reeves and Pfister have a recent work which show that Reed-Muller codes achieve capacity in any binary input symmetric channel. So the Berman codes, about which I did not talk about today, they satisfy most of those properties, almost all of those properties of Reed-Muller codes except the one. So we are indeed interested in seeing whether these codes are capacity achieving in other channels also.
Okay. All right. Thanks a lot, Lakshmi Prasad, and thanks everyone for attending. Satyajit, I don't know if you have any ending remarks or any announcements you want to make.
Yeah, I thank you and Lakshmi Prasad for it was fantastic talk and very well suited for this summer school. I mean,
Thank you.
you took it from very basics to all the way to the very latest of ideas. So that's very much very good. And so this concludes day two with at a very good note. And so I'll inform the participants of the tomorrow's schedule by this night, and then we'll have yet another day. And your talk was another way very well suited. I arranged that way that because Raymond uh,
Yeah.
went through the discrete memoryless channels, so in that sense also students would have another treatment that from your talk. Yeah,
Thanks, Nikhil.
thank you. So yeah, this is you.
See you.
All right. Bye. Okay.
Bye, Nikhil.
Bye.